In the previous video, I said that you can think of a function as any graph, but with the strong condition in that the graph doesn't go back on itself. So just like in algebra, you would use something like this. Let's say 3y equals, let's say 2x plus 7. You see, you would use x and y here to represent a general case. So no matter what you put into x or into y here, this general thing will always be true. You see, x and y allows you to work for a general case. Now, functions allows you to do the same thing, but with graphs. So here, if you're told that, if you're told that I've got a function here, f of x, that means inside your mind, what should be going inside your mind is that you've got a graph here that doesn't go back on itself. Now, if you have a function, let's say f of x, if you have a function, the rough gradient for that function, let's say you've got a function here. Hang on. Let's say you've got a function f of x. Okay. You've got a function f of x. If you want to know a rough gradient for this function here, you can use this. Let's say this is let's say the black line here represents f of x. Okay. And then this purple line here represents another function. You see, just like x and y, it allows you to work for a general case. Here, this f of x here is like one line, and then this g of x is like another line. So by using f and g, we can work for a general case. Well, what we're saying is that for a general case, if you want to work out the gradient, a rough gradient, you can use this. So here, suppose you want to work out the gradient, a rough gradient of this f of x here. You select any a and b. Let's say b is here. Okay. So just looking at the black line, if you want to work out the rough gradient of the black line here, select a and b. So a would be, so this point here is f of a. Okay, and this here would be f of b. And then if you draw a rough triangle underneath there, that will allow you to work out the rough gradient. It won't be exact, but it will be a rough gradient. So here, so you see fb minus fa, that will give you this height here. And then b minus a, that will give you this length here. Now if you get that height divided by the across here, that will give you the rough gradient. You see, by us having a general case here, we can apply it to g as well. Now we've got a function g of x, and we can apply this same rule to g of x here. So select any a, b. Let's say b is here. So this is g of b, okay, and then this here is g of a, and then when you get g of b, take away g of a, that will give you the height of this triangle here, and then you divide it by b minus a. That will give you the rough gradient of this. You see, by you giving a function, this thing here will always work. Now, suppose you give a graph that is not a function. Hang on, let me clear this. So remember this. Okay, well, you don't need to fully remember it. Well, if you get given, let's say a line that is not a function, this is why we have to be specific and say that it must be a function. Suppose you give something that's not a function like this. Now, what's the gradient of this? Let's say b is here and a is here. Okay, a is here. Let's yeah. So normally it would be f of b, take away f of a, and then divided by b minus a. You see, when you come to work out this bit here, f of b, if it's not a function, then it breaks down. You cannot. So here you've got three. Which one do you choose? Well, this one here, f of a, would be here. Well, we can't even use f because this is not a function. So my point is that if you try and work out the gradient here, which point do you use? Do you use this one here, or do you use this one here, or do you use this one here? This is why we have to specify. Oh, it must be a function. So it must be a line that doesn't go back on itself. If you give me a line that goes back on itself, then everything breaks down. So this is why we have to be strict and say, oh, it must be a function. Okay, so functions allows us to work for a general case. Okay.